I'm Luke. And I'm Nathan.
And we made an automated sports net. So this project focuses on improving how volleyball nets are adjusted in indoor gym settings. Currently, most systems rely on manual crank mechanisms, which require time, physical efforts, and manual measurements. Existing solutions include the standard hand crank systems and external measuring tools, but these still rely heavily on human input. So while fully automated ceiling suspended nets, like this one, do exist, they are extremely expensive, typically ranging from $30,000 to $60,000. Our solution aims to provide a much more affordable alternative, which would be around $300, by automating the height adjustment process while maintaining accuracy and ease of use. This system was designed to meet several key requirements. Functionally, it must raise the net to the regulation height of 2.43 meters, and it must operate automatically, allow manual override, and stop precisely at the target height. From a performance standpoint, the system must achieve an accuracy of plus or minus 2 centimeters, complete adjustments within 10 to 20 seconds, and maintain consistent performance over repeated cycles. Safety is also critical, so the design includes an emergency stop, over-travel protection, and a secure locking mechanism during gameplay. Mechanically, we use a worm gear lifting mechanism to prevent back driving, with a load capacity greater than 1.5 times the expected net tension, and a factor of safety of at least 2. Electrically, the system operates from a 120-volt AC source and connects to a 12 to 24-volt DC system to power a hybrid motor. The control system is controller-based with position feedback through an encoder or sensor. Finally, the system is designed for indoor use with a lightweight structure under 15 pounds per pole and a low noise operation. The scope of this project includes the full development of a working prototype. This covers the mechanical lifting system, the electrical powers, components, control system, safety features, and testing and validation. However, certain items are outside the scope, such as outdoor use, commercial production, and multi-height adjustments for different levels of play. So this Gantt chart outlines the full 2-semester timeline of our project. Our first semester focused on planning, concept development, and design, including the preliminary design review and the critical design review. And the second semester focuses on procurement, fabrication, system integration, testing, and final validation. Our work breakdown structure organizes the product into 5 major phases and tasks, which include the mechanical, the electrical, coding, testing, and management. For our billing of materials, we have a railroad cost of $318.21 and a books cost of $254.66. This is under our $500 budget.
So this is the AutoNet. This is our design. As you can see, this is a mounted simulation of what the volleyball hole looks like when you're actually in the gym. This is the existing winch system, and ours is made to attach onto the existing winch system as opposed to replacing it entirely. And so the main important measurement we needed to make was to measure the maximum torque we needed to raise the net to its full height. And so we raised it up to the full height, and we added kettlebells to the crankshaft until it started to move, which ended up being 30 pounds of force on the 4.25 centimeter crankshaft, which ended up giving us a maximum torque necessary of 5.67 newton meters to raise it to that full height. So we chose to go with an EMA 23 stepper motor. We chose a stepper motor because we could control it using its position to ensure it gets to the right height. Because since you're taking the poles down and putting them back out every single day, it's hard to use a limit switch or other sensor to really tell you when it's mechanically at the top. And so with this, we needed a worm gear because that 1.24 newton meters of holding torque wasn't enough to raise so we went with the NMRV30 worm gear because it interfaces directly, it can be mounted, the NEMA 23 can mount directly to the flange of the worm gear using M6 screws. And the other reason is that it gives a better form factor. It allows us to mount the motor horizontally so it doesn't protrude out from the pole and interfere with the play. So we were between a 10-to-1 gearbox and a 21 gearbox. The 10-to-1 gearbox ended up giving us 46% of the holding torque necessary to raise it to the top, while the 21 gearbox only used 23% of the holding torque necessary to raise it to the top. And so we went with 21 because this 23% was more feasible and would limit our risk of skip steps, which would decrease the preciseness of our system. And additionally, the price and size for both models were about the same, so it didn't make any difference on that. And we also included a slip clutch that was mounted between the output of the worm gear and the input on the existing winch. And so this is pretty much to limit the amount of torque our device can output, so it can't over torque the nets and it can't damage the poles or the net itself. And so that works by, once it reaches a certain torque, which this one's adjustable from about 3 to 10 newton meters, so ours falls right in that range, it starts to slip. So instead of the input turning, the slip clutch turns instead, which protects the poles. And so this is our housing design. We have this side plate, which is mounted by 2 screws to the existing winch system. And then we have a battery compartment up here, and then we have vertical venting so that you can create kind of a chimney effect so that when the motor and the motor driver get warm, it can provide cooling to the system. And this is the bottom of the system where we mounted the buttons, because sometimes the winches are mounted relatively high, so we wanted it to be still able to be used by someone who's on the shorter side. And so this will allow them to easily see the buttons. And this is also the worm gear output. It goes through here and is mounted by these 4 holes on both sides. So we have 8 holes holding the worm gear to the housing itself. So we did some preliminary FEA by simulating the 6 newton meters. We decided to be conservative on those 8 mounting holes and using just the 2 holes on the side to keep it in place, which gave us a max stress of about 13 megapascals, and given a max yield stress of about 25 megapascals for the simulated PLA 3D printing material we were using, it gave us a safety factor of about 1.92, which we felt was good enough because there's not really any human safety involved. If the system fails, only the housing would be damaged. And so under the electrical design, we chose an ESP32 microcontroller to run our system, to run our code, to incorporate all the buttons into. And then we chose a TMC2209 motor driver to drive the stepper motor to ensure that it raises correctly every time. And the motor, we also used a 4S light bulb, which gives about 14 8.8 volts nominal or maximum 16.8 volts to the system. And so because this light bulb needed a 5-volt buck converter to power the ESP32, and then we used the ESP32 to also power the motor driver. And so some safety considerations were, because we're using a LiPo battery, if there's some kind of short or something damaging the system, it can create a really high current. And so we put a 5-amp fuse into our circuit just in case that happens, to prevent any excess damage to the wiring or any other parts of the system. And we also have capacitors between the motor voltage and the ground on the motor driver to protect from any back EMF in the system, as well as another problem with LiPos is if they get too low on charge, if the voltage gets too low, they can become permanently damaged. And so we went with a voltage divider using a 100k ohm and a 22k ohm resistors so that we could monitor the voltage using an ADC pin on the ESP32. And that way we can make sure that if once it gets too low, we can put a warning light onto the system to say charge the battery. And if it gets even lower, we'll prevent the system from being used to prevent that damage from the battery happening. We use relatively high resistances so that there's not like an excess current draw just when you're using the system at any point.
All right, so this is our electrical schematic. It starts with the battery in the top left-hand corner, going into our 5-amp fuse, and then into our power switch. And when turned on, it goes into the 5-volt buck converter, and then going down into our ESP32. Main components is we have the 6 buttons. We have the up, down, all the way up, all the way down, calibrate, and an emergency stop button, along with an LED light for the battery to let us know when it's below that tolerance level. Out of the 3.3 volts in the microcontroller processor, it It splits off into the microstep setting 2 and the voltage input in the motor driver, along with the microstep setting 1 and 1 right to ground. And then here's our coding flow chart. Of those 6 buttons, of utmost importance is when the system is running, any of the buttons can be pushed for it to stop. And then to release it from being stopped, you have to hold the all the way up button for 3 seconds for it to be released. So for ethical considerations, our goal is to prioritize user safety. We're including the emergency stop, the slip clutch, and the secure locking systems. We're going to design based on sound design principles and record an accurate height control of the 2.43 meters with a plus or minus the tolerance of 2 centimeters. For integrity and honest reporting, your test results reported accurately and transparently, and limitations and risks will be clearly demonstrated. For responsibility and accountability, our commitment is going to be to ethical and responsible design decisions and consideration of the long-term safety, maintenance, and reliability of the system. For our testing plan, our test setup, we are going to install a prototype on the indoor volleyball court at Wilkes University. We're going to apply the standard net and regulation tension and use the measurement tools height verification. For the testing method, we're going to test the system multiple times. We're going to measure the final height after each cycle. And that's just going to be like what is in a normal system or normal season, so it goes up and down multiple times. For the safety checks, we're going to ensure the emergency stop during the operation. And then for data collection, we're going to log the height, time, and performance results. We're going to compare it against the data against the design specifications. So our plan moving forward in the next semester, we're going to order the mechanical and electrical components, we're going to manufacture the structural parts, and we're going to assemble the lifting mechanism and housing. We're going to integrate the motor, sensor, and controller system. And then we're going to validate the height accuracy of that 2.43 meter height that we were talking about before. We're going to perform the loaded testing cycles. And then from there, we're going to refine the system performance and alignment, making sure there's no fixing all the little mishaps along the way. And then in conclusion, for a project summary, we're going to build an automated AutoNet system. We're going to make sure we're basically taking out the anchoring part of the system. Key achievements our goal is to integrate the mechanical, electrical, and control systems with the $500 budget that Wilkes has given us. We're going to meet the core safety performance requirements needed for volleyball as of utmost importance. And the impact, the main thing is that we're going to improve the quality of life. This isn't like a needed system, but it's something that will make the quality of life better for the players and the referees so that they can get right into the game without having to do set up time before and after. Some acknowledgements. We want to do a special thanks to Dr. Liu, Dr. Bednarz, and Ms. Carrie Chase for all their help this semester with helping us make this new project. And here are our references. Any questions?
Any faculty questions?
So I see you guys are using the ESP32 microcontroller and it has Wi-Fi on it. Are you going to use the Wi-Fi?
So we didn't really think about that when we first designed it, but if we have time, we may consider that next semester. Once we get the system working as a whole, then it might be, we might consider using an app to try to control the net up and down.
Okay, just as a follow-on with that, software development, I didn't see a whole heck of a lot discussed about software development, and so that's a concern.
Yeah, so we decided for this semester we would just sort of outline with a flow chart what we're going to do with our coding and really hit the software development side part of the fall to make sure that we're ready.
So I'll give you advice. Do not trivialize your software, okay? Because that is what is going to, 90% of the project is your mechanical, your electrical, and all that other stuff. The other 90% of the project is software, okay? So just don't trivialize it.
Thank you.
Yeah.
Questions? More faculty questions? Go back to your, when you were talking about the Louis better. Next, the circuit diagram. Yeah, right here. So could you help me understand, like, how are you using those two resistors to tell you, like, how much power the system is actually trying to draw?
Yeah, so it doesn't really measure how the system is drawing. It measures how much voltage is left in the batteries themselves. So with the 100K ohm and 22K ohm, it decreases the amount of voltage at this.
Oh, so it's just measuring the battery
voltage.
capacity,
Yeah.
the voltage, okay.
So for a light bulb, if it gets too low, it can permanently damage the battery or worse. So this is to monitor that.
Okay, so how would you prevent overdrive the system, like overtensioning the system?
Overtensioning, we are using this slip clutch. So it's a mechanical. Once the tension reaches a certain point, this slip clutch will start to turn instead of the input into the actual winch.
So it's a mechanical coupling, kind of a manual. It's almost like a passive system, right?
Yeah.
Okay, so one quick comment, which is instead of using worm gear, I would suggest you to use a planetary gear, which is much more compact and absolutely better performance-wise. Just take a look at that. I think it works better than the worm gear. All right, is it, okay, so you have that, but the system you just described is very similar to ratchet and pull kind of thing, right? Is it? The one you said that avoid overtensioning, that mechanism, is it similar to a ratchet and pull mechanism?
What do you mean by is it similar to like the ratchet?
No, I mean like, is it going to be prevented? Okay, so are you going to use the stepper to constantly hold the torque?
No, okay. So in our loading flow chart here, so once the motor stops, we are going to use the EN pin on the TMC 2209 to disable the motor driver so that it's kind of able to turn, because the winch itself already has a locking mechanism, and the worm gear rods we're adding will also help with that. So once it's raised to the right height, the motor will kind of shut off, so it's not constantly drawing power and it's not constantly.
So basically, even the original existing system, it should be able to hold it, right? Like,
Yeah.
Even just kind of after some time, because hitting by the bolts slowly kind of become this slack.
Yeah, there's already like a worm gear built into the original winch that has a locking mechanism.
Okay, so you will definitely, so you need to control that, because you don't want the stepper to constantly draw power and gets like
Yeah.
not efficient, also like it's not good for the motor as well. Thank you.
Any other questions?
So, can you, I might have missed it when you explained it the first time, so how are you verifying the height? And where does the feedback come in that it says to keep on going up until it hits the height for your
Yeah,
requirement?
we're gonna have a calibrate button. So in the beginning, you can set it up where it'll just calibrate it, and it'll go immediately until it's fully taught, and then it'll run that into memory, and then from there on, it'll run it specifically to that height. So like that many clicks into the motor.
Okay, so you're relying on torque, or you're relying on how far the motor?
The position of
Yeah,
the
position.
system.
Okay. So you're relying on position. So, all right, so that's going to be part of your calibration, is you need to know how far to move it so that it's at the height that you want.
Yeah,
So
the
the
reason
I was gonna say the reason we do that is because like if the neck gets too loose after a while, of constantly bring it up and down, we can recalibrate it if it's not between that 2 centimeter tolerance that we're talking about.
One more quick comment. I really hope you could add like a 2 image switches, really use that as a master sort of protection. Like when everything out how break loose and you still have those 2 image switches tell you you need to stop. Does that make sense?
Yeah, we just.
I mean, it might be mechanical, it might be a little bit hard to do.
Yeah.
Okay.
But we'll look at that. Definitely.
You see what I mean? I really hope you could have 2 image switches at the 2 ends to tell you like what do you actually, you no matter what, you will never go beyond those 2 positions.
Okay.
They brought it up. You guys brought up calibration, and so I'm going to go back to my favorite thing is software. Okay, so where are you putting calibration?
So we plan to make a calibration button this one right here. So it's like,
Where are you handling calibration? Where are calibration decisions being made?
so when you press and hold the button, it's going to raise the step motor and count the number of steps. And once you release the button, it'll store that number of steps in that position as the top position.
And so what's counting the steps? See, this goes back to a lot of this stuff is handled with your software, calibration, this part of software, all of that. So therefore, your software is not trivial. And as Dr. Young had said, stop limits are hard safety stops. Okay, but somewhere along the way, your software is going to have to say, oh, I'm at my position, because you're measuring a voltage, which is telling you that you're out of position or whatever. So all of these, you're measuring something, okay? A step is something, it's a distance, and that's where your calibration comes in. And that needs to be handled in some sort of table, because you said you're putting something in memory. You would use the word memory in your discussions. What memory?
Well, I meant the microcontroller.
Yeah, see, that's software. So very little discussion about software, yet it sounds like software is extremely critical for you. It's just advice, okay? You're going to need help, okay? Yeah.
Thank you.
Any other? Okay, any other questions? All right, thank you.